Right, so this is going to work. Okay, so this is another animation to show that. Right, so laser hits the sample spot and the analytes are dragged off into the mass analyzer. So what you see here is actually the entire mass spectrometer. You've got the mouldy source, so where the ions are produced, and the mass analyzer, which is a TOF, that stands for time of flight. Okay. And the idea behind a time of flight mass spectrometer is if you have ions that have the same energy when they enter a field-free region, so there's no electric field applied in that region, then because they've got the same kinetic energy, half mv squared, the ions with the higher mass will have a lower velocity, and the ones with the lower mass will have a higher velocity, so they'll reach the detector first. So based on how quickly they arrive at the detector, you can determine, because you know the length of the drift tube, you can calculate what their mass to charge is. Okay, let me show you that again. Okay. Time. Okay. Okay, so do the ionisation techniques, are they okay? Happy with them? They're both used in proteomics, and we'll talk as we go through, not today, but in one of the other sessions, about where they're used in proteomics. MALDI is very quick, but you have less confidence in the peptides that you're identifying, whereas electrospray, because it's a continuous process, and you can couple it with liquid chromatography, which gives you the possibility to get greater confidence in your protein assignment. But we'll talk about that more some other day. Okay, so here's a quiz. If you had a protein of molecular weight 10 kilodalton and you analysed it by mass spec, what would you expect if you ionised it by electrospray, and what would you expect to see if you ionised it by MALDI? So I'll let you think about it for a moment. The clue is in the fact that electrospray produces multiply charged ions and MALDI produces singly charged ions. Anybody got an answer? No? Right, I tell you, we'll start with MALDI, because that's the most straightforward, even though it's number B, or letter B. Right, so this is the mass spectrum. Okay, we've got mass to charge, and we've got relative abundance. So if you've got a protein of 10,000 kilodaltons, so 10,000 daltons, and you ionise it by MALDI, MALDI tends to result in singly charged species. So the mass to charge will be 10,000. Okay, strictly speaking, it would be 10,001 because you've added that proton on. Okay, so you would expect to see one peak at 10,000 mass to charge. Or 1, if we're going to be specific. Generally speaking, you wouldn't get that sort of resolution with this. Okay. Now, electrospray is a bit, you're looking confused.
So what's on the y-axis?
Mass to charge, M over Z. So M is the mass and Z is the charge of the ion. Okay. Are you okay? You look confused. No? No, okay. Right, so electrospray gives you... Oh. This pen is running out. This electrospray gives you multiply charged ions. So if you had a protein of 10,000 Daltons and you had 10 charges on it, you would expect to see it at a master charge of 1,000. Okay? So you'd have a peak here, which corresponded to the 10 plus. So the protein with 10 charges on it. Now, you wouldn't just get a single peak, because you get a distribution of charge states. So you would also have a peak corresponding to the 11 plus, and the 12 plus, and probably the 9 plus, and the 8 plus. Okay, so I can't do this in my head standing up in front of you, but so this would be 10,000 divided by 11. This would be 10,000 divided by 12. That would be the master charge. 10,000 divided by 9. Yeah? So these are all the same protein, just in different charge states, so just with different numbers of protons on them. Okay? Does that make sense?
Why is it not just 10 plus? Why are we doing the 12 plus and 11 plus?
Why do you get the distribution?
No,
Is that what you're asking?
no, I'm not really sure. Sorry, it's 10 plus. It's with the 10 kilodalton, isn't it?
Yes.
You would not expect to just have like multiple 10 plus peaks. Is that not what the distribution is?
No, the distribution is. So some of the proteins will have 10 protons on them. Okay. So you wouldn't have a single protein, one protein molecule. You'd have a population of them. So let's say you had 100 or 1,000 proteins of 10,000. The same protein, but you've got 1,000 ions. And some of them will have 10 charges on it, and they'll show a master charge of 1,000, because that's 10,000 divided by 10. Okay. And some of that population of ions will have 11 charges on it.
How do you distinguish between them? Like, if you've got more than one protein, how do you distinguish between?
Well, if you had a protein of, oh dear, let's say you had a protein of 11,000 Daltons, and that had 10 charges on it, then that would appear at master charge of 1,100, and then you'd have 10 plus of your other protein, protein A, protein B, and then you'd have a charge distribution of that as well.
So you just have them double, kind of.
Yeah, you'd have quite a complex spectrum. Yeah.
Why did you use that then? Is it not just easier to use the other one because it gives you one peak?
Right, that's a good question. But what we're getting onto there is mass analyzers and their different characteristics. So some mass analyzers have very high resolution, so they can differentiate between peaks that are very close in mass. Now, it tends to be that the mass analyzers that are compatible with electrospray have very high mass resolution, whereas the time of flight, which you would use with the MALDI, has low resolution. Okay. Now, really, you have to use time of flight with MALDI because the master charge range is another characteristic of a particular mass analyzer. Okay, so with the time of flight analyzer, the mass range is virtually infinite because if it's just a bigger molecule, it will take longer to get to the detector, just take longer to travel that drift tube, the field-free region. Okay. So if you want a higher resolution instrument, it'll have a restricted master charge range. Okay, so then you'll have to use electrospray because most analyzers will go up to, say, 1,000 or 1,100 master charge, but not many of them. Well, really only the time of flight will go up to 10,000. Yes?
Why do you have to use time of flight with MALDI?
Well, because it produces singly charged ions. Because it produces singly charged ions, the master charge of